Hi, Professor.
Hi, how you doing?
Good. We're we were trying to get the random picture working, and
Mhm.
somehow it's not showing like a picture, but it show a frame and then like
Oh,
a
okay, so
small
there must
sign.
be a JavaScript issue. You are correctly getting a good random number.
We are not sure, but
Well,
we use.
you need to, that's what we're talking about today. You need to test out your random number
Oh,
routine
okay,
first before you try to use it.
okay.
Oh, wait, am I showing the right one? Hang on here. Something seems not right here. Developer testing. Well, that's chapter 22. Yeah, okay. I see.
Professor, the password.
Does that seem not to be right? Let me check here real quick. I might have done the wrong one. Okay, so yeah, it's not right. There we go. You could get in there now.
Oh, Professor Scon, you're muted.
How's everybody doing? Last week of classes, you guys ready to finish up and have a long, long winter break? The longest in history. So anyway, today we're going to be talking about testing. Let me, before I do that though, let me, oops, let me bring this up. So looking over our last few days, we're going to be talking testing today, refactoring on Wednesday. I put this final project complete on this date, but you know, mainly you need to have it before the final. So what's again going to happen is you guys are working on your final project. You're going to turn in your GitHub project, all your documentation and your web page, and your program should be running and working when you turn it in. Now, for the final, what you're going to be doing is you're going to be making a presentation, and what I'm looking for in the presentation is a slide presentation on the, you know, your final design of the project. You want to show your architecture, your database structures, and your database design, and the structure of the messages passed between the client and the server, which we did early on, and I want to see what those evolved into. And you know, some of you, based on some of your questions, I realized some of you guys didn't really do that before, and now you're realizing what an API was. What I want to know is your API. How do these subsystems communicate with each other? What are the messages, format of the messages and the responses? And of course, during this final presentation, you're supposed to give a well-orchestrated demo of the whole system. And I want you to show how the system deals with anomalous input, right? I want to, you know, part of this is making a good, robust user interface. Then I want you to talk as a team about give an overview and analysis of the major hurdles encountered during building the system and how you overcame them, right? Again, as I've said before, I want us to be reflective about this. I want us to think about what you learned about working as a team, what you learned about building a more complex system with many pieces, where in many cases you were working in domains that you didn't have a lot of knowledge, and you had to figure out how things worked before you could use them. You know, what did you do? Did you write prototypes? Did you do experiments, etc.? I want you to talk about that. I want you to think about that. And then an overview, a final overview, when this is kind of what I was just talking about in addition, you know, what did you learn about software development, about working as a team, about the challenges of making a good visual interface? And I have a grading rubric. Okay, so that's the final thing is this personal statement, and this is individually from you. You know, only you see me see this, and this is my opportunity to get an individual look into your team. And so I want you to be honest with me. I want an explanation of how you felt your group, how your team worked as a group. How did you interact? Did you do team, you know, programming? Did you have problems that you weren't able to solve as a team? What work do you tell the work that you think each of, you know, the major work that each person on your team did and the percentage of efforts each member of the team did. Now, you know, you may not want to do this, but I would like you to do it. And you know, this is my, you know, just try to be honest. And what would you do different if you had the chance to do it over again? And any advice for me on how I can make things better for you for future courses. And so that's a personal statement that you write up. And as long as you answer all those things carefully, you'll get a perfect credit on that. So again, we're going to come in on December 14th, and we're going to do the presentations one after another. And again, you get about, you know, maybe a half an hour. Let me see, we have well, we actually have 4 teams now. So we basically, you'll get a half an hour, then time for questions, and then we'll move on to the next one. Anybody have any questions about all of that? And I'm trying to remember which day of the week. The 14th is next Monday, yeah. All right. Good. Okay, so let's talk a little bit about testing. Now, I was thinking about, as I was getting ready to talk about this today, and was kind of reviewing my the topics. And one of the things that I want to mention is that if I could have it my way, if we had a real computer science major and we had a real intro to computer science class with, and it had a lab portion, so it was a 0.75, a huge percentage of that would be testing. Learning testing from the beginning is important and is oftentimes glossed over, but it's very important to learn and how to do it. And in my interactions with students, including you guys, I sometimes realize you're doing it backwards. You're writing code and hoping it works, and then much later you find errors in code after you've done a lot of integration, and it's really hard to find those errors. So I like this Dilbert cartoon. Our goal is to write bug-free software. I'll pay $10 bonus for every bug you find and fix. Yahoo, we're rich. Yes, yes, yes. I hope this drives the right behavior. I'm going to write me a new minivan this afternoon. um, and so, you know, obviously he's encouraging people to write in bugs so they can then later find them. The best programming doesn't have many bugs in the first place because you did all the other things. Actually, I want to show something today because I found this very interesting. In the New York Times today, if I can find this, let me see here, yeah, right here. This is very interesting. This talks about the Swiss cheese repository, respiratory, I don't know, respiratory, that's what it is, sorry, virus pandemic defense. And remember when I was talking about Swiss cheese the other day? I did talk about that, right? Remember, we talk about how when you try to make a program work well under difficult circumstances, you have to have layers, and one layer isn't enough to catch all the problems because some things are going to sneak through and you need another layer, and maybe some things sneak through that and you need another layer. And by having enough layers, even though each layer has a problem, by using all of these techniques together, it becomes increasingly unlikely, in this case, that the virus is going to sneak through to the person because they've done all of these things, right? And no one is enough, right? There's no silver bullet. And so developer testing is one of many things that we do. And we want to do all of the things, and we want to do them well, right? Now, when we do development testing, we do them at different levels, right? When we write a unit, just a simple function, we test that function by itself. We write the function, then we write some code to test the function. Now, most of the time, I'm going to bet you don't do that. And you're taking a chance when you don't do that because you might be, you know, you're likely to be using a function that has some errors in it, and it's going to be harder and harder to find the more functions like these that are put together. So it's best to test things as you write them, and then as you start to assemble the pieces, little pieces into components, you test the components. And then as you assemble the components together into a larger system, you bring them in a piece by piece, you add it in and test, add a little bit more in and test. And because you're doing it a little bit at a time, because you're doing everything incrementally, you always know that the error is most likely to be in the code that you just added, right? So that's the type of, these are all the types of testing that you're most familiar with and that you've done at some level or another. Another type of testing is regression testing. Does anybody remember reading about regression testing? What is regression testing?
It was like rerunning errors after you've changed stuff to see.
Right. In general, with regression testing, you build what's called a whole test suite, right? You build a system, you know, but typically what you have is you have a whole set of tests that you've actually written up, and then you can apply those tests automatically to the whole system, and it gives the system a good workout, okay? And so the idea is, let's say you've built a system up to, as you're building a system, you build automated tests for each piece you add to that system, and then every time you add a piece to the system, you write tests for that piece, but you also have all of the tests for all the rest of it, and you rerun the entire test suite. You don't just test the things you just added. Every time you add something or change something, you retest the entire system. With the idea being that it's oftentimes the case that when you add something, it changes something somewhere else in a subtle way that you missed, and you break something else. And so, you know, when I've worked on large projects, for example, where we have, you know, tens of programmers all working on the same system, and we're all contributing and pushing stuff into the system, every night, overnight, the system runs this huge regression tests, and then in the morning when you come in, you see a list of any errors that resulted. And so now you might be wondering, boy, with all this testing and with writing all these test suites, who has time to program? And the answer is you have to work this in to your overall schedule, and it's worth the time you put in. If you go to a company, a major company, like for example, if you go to Microsoft, who has many tens of thousands of software developers, half of those software developers, their only job is to write software to test other software. They write tests. They write software to test software. That's half of the programmers. System testing is testing the system in its final configuration, which includes integration with other software and hardware systems. And one of the things that you need to test at the final system level is things like security, overall performance, test for resource loss. For example, sometimes you might allocate things and not deallocate everything you allocate, and over time the system runs out of memory. Timing problems, and other issues that can't be tested at lower levels of integration. We call these, by the way, these sort of tests, they're tests of an emergent behavior, right? You don't know how secure a system is when you're just testing the pieces. The question is how secure is it when it's all assembled? Same thing's true for performance. You don't know the overall performance of the system without testing it as a whole, right? Just like an automobile, right? You can test the engine, you can test the brakes, you can test the transmission on a test stand, but you don't know really how the car is going to work as a whole until you assemble it all and you take it out on the road and you actually try it and find out what its emergent behaviors are. And sometimes emergent behaviors are surprising, right? For example, perhaps you have a car that you've designed and everything works okay in the pieces, you put it together, you take it out on the highway, and when it gets up to 50, it vibrates like crazy, and you're like, oh crap, right? I didn't know this was going to happen, but it has something to do with the design that you missed and that you didn't see in the pieces. Okay, so let's take a step back again, and that's sort of a top level view. Let's drill down in and talk specifically about testing. In the chapter, talked about two types of approaches for testing: white box or glass box and black box. White box, black box. Black box is a test where the person who tests it is only allowed to use the code. They're not allowed to see how the code works. Okay? Typically, like, you know, when I've worked at companies, we've had I've been a software developer. We pass the code off to somebody else who's not a developer necessarily, and they just test the code and then send bug reports back, right? They have a requirements document. This is what it's supposed to do, and they're supposed to test it to see if it meets those requirements. And they do so without understanding the code. White box, on the other hand, is when we test code and we actually look at the code and say, this is how the code works on the inside. Now let's make sure we write code tests that fully test the code, right? Here you can't do that. If you don't know how the code works, you don't know if you're really testing all the code, because you don't necessarily know how data flows through the code because you don't see the code. Here you see the code, Now, white box, black box, white box, black. What are some of the advantages of one over the other? Like, can you, what are some possible advantages of black box over white box?
Less time.
What's that?
Less time, since
Less
you're not going over the code.
So black box is less time because you don't have to look at the code. So certainly it would take less coding expertise. Like, for example, you could have a black box tester doesn't necessarily have to be a programmer, right? I don't know if that's a key thing, but that's an interesting concept. What else?
The user doesn't know like what inputs it expects, so they might put in like invalid inputs, which would show you like errors in dealing with invalid inputs.
Right. Right. When one of the things that is talked about later in this chapter is the psychological problem of testing your own code. You want your code to work. You're rooting for your code. Your code is like your child, and it can do no wrong, right? And so you even if you don't realize it, you're catering to the software. You remember writing the code, and you put inputs in because that you know how they're going to be handled, and so it works, right? You're avoiding the tough problems because you want everything to be okay. And so, there's an advantage to not knowing what's going on inside the code from a psychological standpoint. Now, what about white box? What can be some of the advantages of the white box approach?
Better understanding of the code.
Right, you understand the code, but how does that help out?
When like errors come up, you probably like know what the like issue is, and it's faster to solve the problem.
Well, yeah, certainly when you are in the process of not just finding the bugs, but fixing the bugs, you need to know what's going on in the code, right? But when we're just thinking about finding errors, what might happen with black box testing that might cause you to miss some errors?
Maybe because you know what the code's supposed to be able to do, you'll be more able to test all of the features.
That's right. That's better, right? That's, the idea is if you know how data flows through the code, you can pick tests to say, well, I want to pick code that goes through this way, and I want to pick code that goes through this way. And in short, I want to make sure that there's no code that doesn't get tested. You can do that if you can see, right? I mean, you're not really testing all the code if you don't put inputs in that use all the code, right? If somebody were to ask you to fully test Microsoft Word, which is a monstrous program with lots of features, right? How would you ever know if you'd actually used all the code? And, because you'd have to go through all the different menus and try all the different things. And you would never really know if you got it all, because there's so many different options, and you don't know which options use what code. Okay, so we were just talking about why programmers don't like testing. Testing runs counter to the goals of other development activities. In other development activities, you want to make it work. In testing, a successful test finds a bug. And you don't want to find bugs. In fact, as somebody who's worked as a developer, when other people have tested it, it's always a little irksome. You're always a little bit pissed off when somebody comes to you and says, I found a bug in your program. You're like, I don't want to hear about it. It's got to be somebody else's problem. or you're being a nitpicky, right? Testing can never completely prove the absence of errors. Testing only proves the existence of errors, right? If you find an error, you proved an error. If you don't find an error, you just prove that the tests you did didn't find an error. You don't prove that the software doesn't have any errors in it. Very hard to prove the complete absence of errors. It's possible, but nearly impossible for any program of high complexity. It turns out that testing by itself doesn't improve software quality, right? It doesn't do anything other than show you that problems exist. It doesn't even tell you where the problems are at, right? So you can test all you want, but unless it's coupled with finding errors and fixing them, it doesn't do anything. So it seems like a waste of time. And testing requires that you assume you'll find errors in your code. Now, what's really interesting is that the bigger the project, the percentage of the time spending testing here's the overall development of the time here. So notice system testing gets a little bit bigger as the project size gets bigger. This is the number of lines of code, 2,000 to 500,000. Integration goes up, obviously, as you have more pieces to integrate. Turns out developer testing actually goes down as an overall percentage of the project effort. Now, that, you know, we're talking percentages here. We're not talking amount of time, right? This project may take 5 hours, and this may take 500,000 hours. So if this takes 5 hours, maybe this is an hour and a half, and this little chunk is still, you know, 50,000 hours. It's still a lot, right? But as the overall percentage, it goes down. But what actually goes up is these other things that are part of building a system. Now, so testing during construction, you generally write a routine or class, desk check it manually, and then you review it, and then you test it. Now you should test each unit thoroughly before you combine them into the others. If you're writing several routines, you should test them one at a time. And if you don't do that, if you write a bunch of routines and then you throw them all together and try to test them, it's very hard to find the error because there's a lot more code where the error could be in. But if you test each one and then you test them together, adding them in one at a time, add one test, add one test, add one test, it's going to be a lot easier to find the bugs. And of course, if you do regression testing for this, you might find hidden bugs that are caused by other code that you added in. So what's our approach to developer testing? First and foremost, it needs to be requirement driven, right? i.e., don't just think about, well, I have these inputs and I have these outputs. Think about what the actual requirements of this piece of code are going to be that were presumably defined when you wrote your design, and you actually write your tests to test based on the requirements. In fact, in some situations where people really want code to be well done, before you write the code, when you're writing the design, you'll look at the requirements. Actually, when you're writing the requirements, you will write, here are the possible input. Here are some example inputs. Here's some good inputs and what the output should be. Here's some bad inputs and what the output should be, right? And you actually design the tests before you write the code. Anytime you write tests before you write code, that's called test-driven development. And many shops do that. Test each relevant design concern to make sure that the design has been implemented, right? We have the requirements. That's the stuff we write before we even design it. Then we design it, and the design has requirements, and we want to test our design. Plan the test cases for this step at the design stage or as early as possible. Again, the earlier you design your tests, probably the better they are, because you're actually thinking about what the inputs and the outputs can be. In fact, it turns out oftentimes, if you don't write good requirements and you do a design and then let's say you pass the code off to somebody else, if that person doesn't really know what the requirements were, it's unlikely they're actually going to write the software correctly if there's any vagueness. And so having good designs and having good sets of requirements, and even perhaps having good test cases before you write the code, can help reduce that possibility that you're not writing, you have perfect, it's very easy to write code that works perfectly according to what's in your head, but that might not be what's needed, because what was in your head wasn't right. Use basis testing to add detailed test cases to those that test each requirement in each design, and then have a checklist for the kinds of errors you made on the project to date and have made on previous projects. It turns out we learn a lot from our own errors and from other people's errors. We learn a huge amount. And this is why, by the way, it's really valuable to take your time to understand an error rather than to just try to make quick changes and hope that it'll work without really understanding what went wrong. Like, oh, everything seems to be off by one, let's just add one, right? No, what went on? And so, when you look at other people's code and you help them, you learn about the types of errors are made. I would say I hope you guys will agree with me because I help you guys, but I'm really pretty good at finding errors. One of the reasons is I've been finding errors in students' program for 30 plus years. And so over time, I've learned a lot about errors. I've learned a lot about the errors that I've made. I've learned a lot about the errors that you guys make, and this informs me. And you can use that information if you keep track of that and say, in this project, we keep running up against these 6 types of errors. Let's make a checklist. And every time something's not working, let's look through that checklist and ask ourselves, could it be one of these sorts of problems? And then we both learn from them, but we also reduce the time in finding them because we're realizing the sorts of things we tend to do wrong. Now, limitations of developer testing. Developers' tests tend to be clean tests. What does that mean? What's a clean test?
And that's what you were talking about before, where we tend to not want to break the code, so we write tests that are fairly safe.
That's right. We don't write tests that push the boundaries, right? So developer testing tends to have an optimistic view of test coverage too. They think, well, I think I've covered it all. Developer testing tends to skip more sophisticated types of test covering. And so what you really want is you want 100% statement coverage. That means you run every statement, and 100% branch coverage, which means you take every possible branch through the code. So now, one of the things that comes up from time to time is exhaustive testing. Can we test everything? Well, let's think about this. So let's say we have just a database and we actually want to do exhaustive testing. If we have a name that's 20 characters, an address that's 20 characters, a phone number that's 10 characters, and then, of course, a name, we're just assuming uppercase or lowercase, let's say, that's 26 to the 20 possible names, 26 to the 20 possible addresses, 10 to the 10 possible phone numbers. And so the total is approximately 10 to the 66, which is ridiculously big, right? You're never going to test all those possibilities. And frankly, you don't need to. So exhaustive testing is neither possible in almost all cases, nor does it make any sense, because why would, you know, two slightly changed names change the input? That's just not a good, change the overall outcome. That's not a good idea in general. Now, another approach to testing is data flow testing. And this is kind of cool. It's thinking in terms of how data flows through your program, and think about things that tend to be error prone. And you can actually do this, and compilers will oftentimes do this for you. They will show you possible errors. For example, if you use something before you define it, a compiler, you know, or even an editor, right? We see this in Replit, where the editor will tell us if we're using a variable that hasn't been defined yet. If we're trying to use a variable that hasn't been defined, it can see that because it does an analysis of our code, and it's doing that using data flow testing. It's actually looking at when things are defined and when they're used. So it turns out data can exist in three states. It can be defined or not, it can be used or not, and it can be killed or not. And defined just means we've created it, we've initialized it, but we haven't used it. We may have just actually not even initialized it, but we certainly defined it. Used it, right? We used it in some computation, and killed it means it doesn't exist anymore. Now, most of the killing that we do so far is when we create a local variable in a routine. When we leave the routine, local variables are killed, right? But there's other ways of creating and killing data. For those of you who've had, for example, data structures, you know that you can create things using a new, and that you can eventually dispose of them using a free, right? Some of you have seen that. And many languages have the ability, in fact, almost all languages have some ability of dynamically allocating and then releasing memory. Now, the problem with killing is sometimes we get rid of something, but we continue to try to use it. That's always bad. Another problem is we might try to use something before we've designed it. And this is where flow comes in. Now let's look at, and we're going to see this in a second, but first let's talk about routines. We talked about variables. Variables can be defined, used, or killed. Routines have a state, right? We can have a state where we've entered a routine. We can have a state where we've left the routine, right? And so when we enter the routine, when the control flow enters a routine, and then a variable might be acted on within that routine, or we might have a working variable that's created in the routine. And when we leave the routine, we oftentimes are getting rid of variables, right? Because they're going out of scope. So it turns out that there's suspicious combinations of data states. For example, if we define something and then define it again with doing nothing in between, probably we did something wrong. Why would we define something and then define it again but never use it in between those two defines? It doesn't make sense, right? Or what if we defined something and then killed it but never used it? Or what if we entered a routine and then the first thing we did is we killed something? Or what if we entered and then we used before we defined? Or what if we killed something twice? That doesn't make any sense. Or what if we tried to kill something, we killed something, but then we tried to use it? That means a variable doesn't exist anymore and we're trying to use it. Or finally, what if we tried to use something and then we tried to define it? And the point is we can do code analysis to look for these sorts of problems that while they may not technically be an error, they're very suspicious, and oftentimes they mean the code certainly isn't well written. So let's look at a flow testing here. Here we have F condition 1, we do this, else we do this, F condition 2, we do this, else we do that. So let's look at this. How do we cover every path? Well, let's think about it. Condition 1 can be true or condition 1 can be false. Condition true can be true, or condition 2 can be false. That gives us how many possibilities? 4, right? So we can go through that, right? If condition 1 is false and condition 2 is false, we execute these 2 statements. If condition 1 is true and condition 2 is true, we do these 2 statements, the first 2. If 1 is true, we do this, and 2 is false, then we do that. If 1 is false and 2 is true, we do this second one, and then we do this first one. So those are 4 paths through this code. So if we're really going to test our code, we probably want to test all 4 paths. And so we have to come up with data to do that. Of course, that's going to require white box testing. There's another concept in programming that really helps us reduce the number of tests. Remember earlier when we talked about the fact that, well, if we want to test, you know, we have name, address, and telephone number, and we had 2 to the 10 to the 66 possibilities. Well, most of those possibilities are identical to each other. Now, this is a very mathematical concept when we talk about equivalence partitioning. It's the idea of we have a set of data, but we can break it up into partitions. We can slice it up into pieces, and we can say within each partition, all of the data is essentially the same, right? It's going to achieve the same results in the code. And so if we can find the different partitions, what we want to do is we want to make sure we test from every partition and don't leave any of the partitions out, more than we want to make sure that we get all of the things in one partition, which is not very useful. So here's an example. Let's say we have a password that must be between 8 characters, a minimum of 8 and a maximum of 12. Well, then we have 3 partitions. We have the partition where things are less than 8, the partition where they're 8 to 12, and the partition where they're more than 12. We want to try things from all 3 of those, right? Here's another example. I mean, okay, wait, no. So now when we test partitions, we not only want to test things within the partitions, but we want to look carefully at the boundaries and say, oftentimes things go bad on the boundaries. So we could have test cases where things are less than 8, test when they're exactly 8, test when they're between 9 and 11, test when they're exactly 12, and test when they're greater than 12. So now we have really 5 different tests that we want to pull from, and we want to make sure we pick cases from each one of those. Here's another example. Let's say we have a function where the input has to be 1 to 1,000. Well, once again, we have 3 partitions. We have the partition where there's less than 1. If it's an integer, a positive integer, then 0, 1 to 1,000, and then 1,001 or more. Now this gives us, obviously, we want to test from each of those. So test case 1, pick things that are from 1 to 1,000. Test cases 2, pick things that are between 0 and 999. So consider test values, just below the extreme edges. So let me go back. I was getting ahead of myself. We want to consider test data right on the boundaries, and then we want to pick conditions just adjacent to the boundaries. So test case 2 is just below, and test case 3 is just above. So that tests right around the boundaries. Okay, so you want to think about those issues. Now, another thing we want to be able to do is we want to be able to sensibly test inputs. This is called error guessing, okay? And it means creating test cases based on guesses about where the program might have errors. A lot of this comes from experience. You might say, you know, this is the kind of thing that often causes problems, so let's try these sorts of things. Again, we kind of talked about this before, but boundary errors, you always want to look at your boundaries. and test around the boundaries, because that's a common place for errors, because maybe you used a less than instead of a less than or equal to, or a greater than or equal to instead of a greater than, or maybe you just compared it to the wrong number by 1. So there's different types of classes of bad data: too little data, or perhaps no data; too much data; the wrong type of data; invalid data types; the wrong size of the data; it's too big or it's too little; or data that's not even initialized. These are all things that you want to look for inputs coming into a routine, or perhaps inputs coming in from a user or a file or a network connection. And so we can classify the different types, and then we can test each of the different types. So that's bad data. Good data. For good data, test the nominal cases. In other words, test normal, typical cases. Don't assume that's going to work. And so nominal cases, middle of the road, expected. Test the minimum normal, maximum normal, and then oftentimes you also want to test compatibility with old data, because it's not uncommon at all when you write a system and you made a new version and you want it to work with new things, but it also has to work with old things. And that can become pretty tricky, very tricky and very interesting. So one of the little tricks you can do that sometimes you may not realize is that use numbers that are going to help you make testing easier. For example, for a salary, you might pick 60,000 rather than 62,446. How does that make it simpler?
If you like wanted to check that they were getting the paid the right amount over a long period of time, it's easier to figure out what like 5 times 60,000 is than 5 times 62,000, yada yada.
Right. So errors show up if you just type in random numbers and then the results are random numbers. Unless you do lots of work with a calculator or something, you're going to get confused, right? But if you're putting in nice, even values and then weird numbers come out, then you have to ask yourself, well, what really happened, right? Now, one of the interesting things about errors is errors are rarely evenly distributed, right? It's not like errors are put into the cookie batter and stirred carefully throughout. Errors are like lumps, right? They show up in certain places and they don't show up evenly everywhere. For example, Casper Jones reported that a focused quality improvement program at IBM identified 31 of 425 classes that as error prone. The 31 classes were repaired or completely redeveloped, and in less than a year, the consumer reported defects against IMS were reduced 10 to 1, so a tenfold improvement by working on what? 7% of the classes. Customer satisfaction improved from unacceptable to good, right? So they didn't have to rewrite the whole thing. You know, presumably they had a couple of bad programmers who were doing bad work, right? Or there was some bad design decisions that were made, right? And so sometimes a system will seem horrible, but it can actually be fixed with not that much work, as long as you realize that we have to find where the errors are really at. And if you find one error in a particular routine, you maybe want to take a really close look at that one routine and the code who wrote that one routine, frankly. So most errors tend to be concentrated in a few highly defective routines. 80% of errors are found in 20% of projects, classes, or routine. 50% are found in 5%. So it's not evenly distributed. I'm not going to really talk more about this, but let me see. since we're almost out of time here. Now, I just want to see what, in the few minutes I have left, because I definitely don't have. Okay, a couple things I want to talk about. One of the things that we can have a problem with is we can have a problem in the testing itself. And sometimes you see and get an error and you're like all concerned about this error, and it's actually an error in the test. So you always want to take a step back and make sure things are sane. So here Dilbert says, I spent a week writing a test script for our product. And Wally says, I wrote a test script to test Dilbert's test script. Your script was almost perfect. Keep up the good work, buddy. So it turns out that test cases are often more likely to contain errors than the code, because frankly, probably when we're writing the test, we're not being as careful because we know it's not real code, or we don't think about it as real code. We think about it as something we're just throwing together to test something else, right? One of the things I wanted to, I wanted to talk about this in the last few seconds. So one of the things that you can do when you have really weird errors that you're trying to figure out, you have this big system, and let's say funny numbers are coming out at certain places. Now, what you could do is you could put some funny value in all unused memory. For example, maybe you do hex AB in every byte that's not currently being used. Well, then if AB shows up in something that's supposed to be, that's being used, you know, oh, I'm using some uninitialized memory, right? You can do little tricks like that to mark things. I guess we're out of time. Okay, keep working on your projects. I've been talking to some of you, and I'll have office hours today from 1 to 3. And take care, stay healthy, and I'll see you.
Bye.
Thank you, Professor.